Welcome to the deep dive. Today we're tackling multi-leader replication in distributed databases. If you're aiming for those senior software engineering roles, especially the ones with tough technical interviews, understanding how to build systems that can handle loads of writes and stay online, well, that's absolutely key.
Exactly.
We're going to dissect different ways to set this up and some of the curveballs you might encounter.
Yeah, you really need to be able to not just name these concepts, but actually discuss the trade-offs, the potential pitfalls. It's about showing you really get what's happening under the hood when multiple nodes are taking writes.
Okay, so at its heart, multi-leader replication means we have several databases, several leaders that can all accept write operations, not like the single primary setup. But how do you actually connect these leaders?
There are a few common ways, right? Different network structures.
That's right. Think of them as blueprints for how the nodes chat with each other. One approach is the circular topology. You can imagine a ring where each database server only replicates directly to one neighbor.
Okay, a ring. And updates flow in just one direction around that circle.
Like passing the baton in a relay race, but with database changes. So if a node gets an update, it applies it, then hands it off to the next one in line.
Pretty much.
How do we stop an update from just going around and around forever, though?
That's a crucial point. Each node in this circle gets a unique ID. So when a write happens, it gets stamped with the ID of the node where it originated.
Okay.
As it travels, each node processing it might also add its ID. So when a node sees an update that already has its own ID on it, it knows, okay, I've seen this before, and it can just ignore it. That breaks the loop. It's a pretty clever way to ensure propagation without those infinite cycles.
Got it. A digital passport for each write, basically. Okay, another setup you mentioned was the star topology. That sounds like it has more of a central point of control.
Precisely. In a star setup, you have a central hub node, and all the other database nodes, you can think of them as satellites. They primarily talk to this central hub. So if a satellite gets a write, it usually sends it to the hub. Then the hub takes care of distributing that update out to all the other satellites. And this can even be generalized, extended into more of a tree-like structure with hierarchies of nodes forwarding updates.
That central hub in the star setup, though, it sounds pretty critical. If that goes down, it feels like the whole system could have a really bad day.
You've absolutely hit on a significant trade-off there. Both the circular and the star topologies can be vulnerable to single points of failure.
Right.
In a circle, if one node fails, it breaks that chain of updates. In a star, if the central hub goes down, well, the satellites are basically isolated from each other.
Yeah.
And often recovering from that requires manual intervention, rerouting traffic, bringing new nodes online, configuring things. That's a key thing to consider.
Definitely something to bring up in a technical discussion, like in an interview. You'd want to mention those failure modes.
Oh, absolutely. And you probably also mentioned that in practice for star setups, you often see things like sentinel processes or automatic failover mechanisms for that central hub. It adds complexity, sure, but boosts resilience. It's that classic trade-off.
Makes sense. So what's a more resilient alternative then? You mentioned an all-to-all topology. That sounds, well, like everyone talking to everyone else.
Exactly right. In an all-to-all setup, every single database node directly replicates to every other node in the system. Think of it like a fully connected mesh network.
Okay.
If one node gets a write, it just sends that update directly to all the others.
Okay, so no single point of communication failure there, which sounds like a big plus for reliability.
Yeah.
But with all those connections, doesn't that introduce a ton of overhead?
Yeah.
Or other complexities?
It absolutely does. You gain much better fault tolerance, obviously, because there are multiple paths for updates to travel. But the sheer volume of network traffic, the number of connections you need to manage, it can make the system more complex and potentially increase latency. But there's another really interesting challenge that can pop up, especially in an all-to-all setup, although it can happen in others too. The order in which write operations arrive at different replicas.
Right, ordering issues. Yeah, I could definitely imagine that causing some major headaches. Can you maybe walk us through a scenario where that goes wrong?
Sure, let's take an example. Imagine client A inserts a new row, let's say key X, value 1 on leader 1.
Okay, new row X.
Almost simultaneously, client B updates that same row, key X, maybe increments the value to 2, but does this on leader 3.
Okay, different leader, same row.
Now picture a third leader, leader 2. Due to network timings, maybe leader 2 receives the update instruction from leader 3 set value to 2 before it receives the initial insert instruction from leader 1.
Yikes. So leader 2 is trying to update a row that, as far as it knows, doesn't even exist yet.
Exactly. You're trying to apply an update to a ghost row. That's a recipe for totally inconsistent data across your replicas.
Wow. How does this happen in practice? Is it just network lag?
It largely boils down to replication lag, just the time it takes for a write to physically travel from one leader to another, plus variations in network speeds, congestion, the usual network gremlins.
Right.
Some connections might just be faster than others on any given day, leading to different arrival times for what should be a logical sequence of events. Lag might be tiny milliseconds within one data center, but could stretch to seconds if you're replicating across continents.
So just slapping timestamps on everything probably won't solve this perfectly either, right?
Mhm.
I remember hearing that clock synchronization across different machines in distributed systems is notoriously difficult.
You're absolutely correct. Timestamps seem like an easy fix, but relying only on them for strict ordering across independent machines is super problematic. Why?
Yeah.
Because clocks on different servers are almost never perfectly in sync. There's always some clock drift happening.
This feels like it gets right into the idea of causality, doesn't it?
Mm.
Like the update depends on the insert having happened first.
Precisely. The update is causally dependent on the insert. There are techniques, like version vectors, that exist to help track these causal relationships. They help ensure that dependent operations are applied in the correct order.
Version vectors.
Yeah, but the challenge there lies in the metadata overhead they introduce and the complexity of comparing and merging these vectors, especially across a large number of nodes. It can impact performance. It's another one of those trade-offs. And a key reason why some systems might actually opt for weaker consistency models, which is definitely something you discuss in those technical interviews.
So are you saying not all multi-leader systems actually guarantee this causal consistency out of the box? They might just let inconsistencies happen.
That's a really critical point. Some systems might not fully enforce causal ordering, or they might not even have robust ways to detect these kinds of conflicting writes. You absolutely have to dive into the specifics of the database system you're considering. Read the documentation carefully, understand exactly what consistency guarantees it provides, and thorough testing under various network conditions is just essential to try and uncover these potential ordering issues before they bite you in production.
That's definitely something to probe during system design discussions in an interview setting. Okay, just to be absolutely sure we're clear on terminology here when we talk about these replication topologies, the rings, stars, all-to-all.
Yeah.
We're talking about how the database servers communicate updates between themselves.
Yes,
right?
correct.
This isn't the same thing as, say, a star schema that you might use in data warehousing, which is about how you structure your actual data for querying.
Exactly. That's a very important distinction to make, especially in an interview. It shows you're precise with your language. A replication topology is about the communication pathways between your database instances to keep data synchronized. A data model, like a star schema, is about the logical organization of your data within a database. They're really orthogonal concepts. You could easily have an all-to-all replication topology, but still organize your data using a standard relational model or a document model, or even a graph model inside each node.
Okay, that clears it up.
Mm-hmm.
So to kind of wrap up what we've covered in this deep dive, we've looked at different ways to architect multi-leader replication, circular, star, and all-to-all topologies. Each has different trade-offs, right? Complexity, fault tolerance, potential single points of failure. And we've really highlighted this significant challenge of ensuring writes get processed in the correct logical order across all those leaders. Because if they don't, you can end up with inconsistent data.
Precisely. And for anyone prepping for those senior software engineering interviews, being able to articulate these different topologies, discuss their pros and cons, and really explain the complexities around write ordering that demonstrates a strong foundational understanding of distributed systems. You should definitely be ready to discuss these trade-offs and how they might influence your design choices in different application contexts.
Definitely. So here's maybe a final question to mull over, especially as you're preparing for those technical discussions. Considering the trade-offs we've explored, fault tolerance versus complexity, the ordering challenges in what types of applications might you consciously choose an all-to-all topology, even with its complexities? And conversely, when might a simpler setup like circular or star actually be the more pragmatic, maybe even better choice?
Good question.
Yeah, think about real-world examples, the specific consistency needs, the availability requirements of different systems.
That's our deep dive for today. Thanks for joining us.